Hello, I welcome you all to this another interesting screencast. We are going to be solving this engineering mechanics problem, and it reads determine the shear and moment as a function of x, and then draw the shear and the moment diagrams. This problem is coming from the engineering mechanics statics textbook, 13th edition by R.C. Hibbeler. So we have a distributed loading on a cantilever beam. This is rectangular in shape. So let's find an equivalent force which will just be acting at mid-span of this particular beam. Okay, mid-span of the distributed loading. Okay, which also coincides with the span of the beam. So this length here is just half of 3, which is just 1.5 meters. So let's find this loading. This loading, let's call it F, which is just going to be equal to the area under the loading diagram. So this is 3, the length of the loading times the load itself, the peak, which is 2. So this gives us a 6 kilo newtons. So let's draw the free body diagram. Like we said, the cantilever is fixed at A, therefore expect AY, we expect AX, and then we expect a moment which is anti-clockwise, right? So we expect it to be in this direction like so. Okay, so this is anti-clockwise, right? Right. Let's apply the equations of equilibrium quickly. So summation of moments about point A equal to 0, anti-clockwise being our reference. What we have a 6 times 1.5. This is a positive moment anti-clockwise. What else? We also have a couple, okay, at the very end here. Let's call this point here B. We have a couple moment there, right? Of magnitude 15, and this clockwise, therefore it's negative. Okay. What else? Then we have MA equal to 0. Therefore, our MA is just going to be equal to, let's calculate, 6 by 1.5 minus 15. This gives us MA equal to 6 kilo Newton meters, right? 6 by 1.5 minus 15, yes, 6. Great. And then we have summation of forces in the y equal to 0, going up in our reference. What do we have? We have ay minus 6 equal to 0. Therefore, our ay is just going to be equal to 6 kilonewtons. We have summation of forces in the x direction equal to 0, like so. And we know that ax is just going to be equal to 0. Right. So let's make a section of this beam so that we find these equations, shear equation and moment equation, which both are going to be functions of x. So we'll make a section where I've just drawn a green line. So we'll have a left-hand section, and the right-hand section. In this problem, they want us to use the left-hand section. But when this is not specified, you choose the section which is simpler for you. Okay, great. So let's go ahead. There we go. So let's imagine that is our section. And then we have a distributed load. That section will come with a distributed load and whose magnitude is a 2 kilonewton per meters, and it will have its own equivalent force. Okay, and this force is going to be equal to let me draw the distance first. So we'll have this distance from there to there. Since this length here is equal to x, we are moving from B to this point, we called it B, from B towards A, and then here we have a couple moment of 15. Therefore this length here is going to be equal to half of x, which is just 0.5 x. And then this load here, this load is going to be equal to F equal to the load under, the area under the load diagram. So what's the length is x, and what is the value of this distributed load is 2. So it is going to be 2 times the length, which is x. Therefore it is 2x. Okay, and then at this point here we expect, let's call this point 1. We call it 1. Let me use black. We call it 1. So we expect a shear force V1 and a moment M1. So this is about it. We've replaced everything that we need to. Let's do the calculation. So summation of moments about point 1 equal to 0. What do we have? We have a minus 15. What else? Then we have a plus 2x. 2x times 0.5x. Then plus m1 equal to 0. Yes. Let's go up. So that we finish what we've started. Great. So what do we have? Therefore, our m1, which is a function of x, is going to be equal to minus x, because 2 by 0.5 is just a 1. Therefore, we just remain with x squared plus 15. Is that okay? Of course. Alright, then we have summation of forces in the y equal to 0. What do we have? We have minus 2x minus v1 equal to 0. Therefore, v1, which is a function of x, is just going to be equal to minus 2x. Okay. So we have two equations, and the span that we are looking at is just continuous. Okay. Again, this is a simple problem. Alright. So let's prepare our lines neatly. We prepare our lines like so that we start drawing the shear force diagram and the bending moment diagram. So this is our shear force diagram. This is our shear force diagram. This is the bending moment diagram. Okay. We have positive up, negative down, positive up, negative down. Okay. So what is our equation for shear? Is minus 2x. So this is a linear equation. A linear equation, it has a gradient which is 2 and is negative. Okay. So at B here, at B, when we look at the boundary conditions at B, of course the equation just tells us that we just need to go ahead and do our work. Alright. So we are starting at B. We said negative slope. So let me move this up. I have a little bit of space. Since this is coming up, maybe I move this maybe up to somewhere there, right? I think so. Great. So negative, so this is just going to be constant throughout, like so. This is fine, like so. Because this value here, we have this value here of 6 or negative 6 kilonewtons. I didn't indicate this. Ay, we found it as 6 kilonewtons. Ma, we found it as 6 kilonewtons meter, and this was just equal to 0. Of course, then we have a closure here like so. Alright. And this is negative. For the moment, we have a positive value at B when x is equal to 0. So let me move this a little bit down. I move this a little bit down, like that. Okay. So at B, we have when x is equal to 0, we expect a value like so, which is of magnitude. This one is of magnitude what? 15 kilonewtons meters. Then we have, and then later on, when x is equal to 3, so this becomes minus 3 squared, which is minus 3 squared, which is 9, so minus 9. So we have a minus 3 squared plus 15. What does this give us? Minus 3 squared plus 15 gives us a 6. Okay, this gives us a 6. Alright, so from 15, then we have this quadratic. Okay, so we expect this function to open like this. Well, I have some space here. This looks alright, maybe somewhere there like this. Okay, alright, so it's quadratic, negative. Okay, so therefore I expect this behavior, if it's quadratic, it's going to go like so. Alright, we said it's going to be at the very end, it's going to be 6. Okay, so it will go something like quadratic. Okay, 6. Alright, then here it is going to interact with an internal moment here of negative 6. kilonewton meter. Okay, so then when they interact, then we are going to have a closure. We'll have a closure like this, right? So this point here is 6 kilonewtons meters, and this is a positive moment, right? So it's like we are done with everything. We have the function moment there, which is a function of x, and we have the shear function there, which is also a function of x, and we have the diagrams. I think this is about it, and I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.